Viewers, welcome back to this channel. So in this video we are going to be proceeding with a topic that we have already started. Now this is the third option of this video and it's for physical equilibria. Purposely we are going to be looking at non-ideal solutions. So you are advised to subscribe to the channel for keeping updated whenever a video is being uploaded. Now for non-ideal solutions, now in the previous videos we are looking at mainly ideal solutions. Now we want to see, I remember that ideal solutions are the solutions that obey Raoult's law. Now why are there some solutions that do not obey Raoult's law? So this is the explanation for such solutions, and those solutions are called non-ideal solutions. So in this question we are asking, explain why some of the liquid mixtures do not obey Raoult's law. And the reason for that is the reason number one, that what you should note is that there is a difference in the magnitude or strength of the forces between like and non-like molecules of the components present in the mixture. And as a result, due to the difference in the forces and the structures, the liquid molecules of the mixture tend to escape into vapor phase. However, some are hindered, their escape tendency is hindered, resulting into giving us a vapor pressure that is either lower or greater than that predicted from Raoult's law. So you are saying that, explain why some of the liquid mixtures do not obey Raoult's law. So the reason for that, in a statement form, we have said is that due to the difference in the molecular structures of the components of the liquid mixture, and we are saying that the forces of attraction formed between molecules in the liquid mixture, that is to say, between the unlike and the like molecules in the liquid mixture, happen to be different in strength or magnitude from those molecules between the pure and separate components. So we are saying that to overcome these forces, the molecules in the liquid mixture, if you read this word properly, to overcome those forces, molecules in the liquid mixture, they are going to tend to escape into vapor phase. Now, as they're escaping into vapor phase, there will be a change in either volume or heat, and finally, either a higher or lower vapor pressure than that expected from Raoult's law is exerted. Like I've explained, these two non-ideal solutions are going to be formed when we mix two different liquids, and those two different liquids are going to be liquids, each of them having different structures. Now, on combining those liquids, each of them, the forces formed between them are going to differ in magnitude compared to the forces between the pure and separate components. Now, when they differ in magnitude, they increase the escaping tendency of liquid molecules. They either increase or decrease the escaping tendency of liquid molecules of the mixture into vapor phase. And in such a case, a solution will end up exerting a vapor pressure above itself, which is either greater or lower than that expected or predicted from Raoult's law. Now we are saying that note, and we are noting the following. We are saying that a non-ideal solution refers to a solution that does not obey Raoult's law of vapor pressure. Now I want you to notice that when you are defining these definitions, you must add all the characteristics. The definition should not be as short as presented in this work. So we shall be looking at the characteristics of non-ideal solutions, and you must include each of them, like what we looked at here. So we are saying that there are two types of deviation from Rorty's law, and one we have looked at positive deviation, and the other we have looked at negative deviation. Now, as you are hearing the names, note that for positive deviation, vapor pressure above the solution is going to be higher, and for negative deviation, vapor pressure above the solution is going to be lower. Now, as we are saying that positive deviation, how can we define positive deviation? Like as I've defined, for positive deviation to occur, when two components, two liquid mixture components are being combined, we expect them to have a higher vapor pressure. We expect the solution that is being formed to have a higher vapor pressure. Now, why does that happen? The high vapor pressure happens in such a way that for positive deviation, when we mix two components of the mixture, the forces of attraction that are formed between unlike molecules are going to be greater in strength or magnitude than the forces between the pure and separate components present in the mixture. But let's first look at the definition. So according to the definition, we are saying that positive deviation is a deviation that occurs when the vapor pressure exerted by the solution. Remember, the solution is formed after mixing the two liquid components, is greater than that predicted or expected of an ideal solution or predicted by Rorty's law. Now I want you to remember it's the ideal solution that obeys Rorty's law, and non-ideal solutions do not obey Rorty's law. Now under non-ideal solutions, we have solutions that show positive deviation and we have solutions that show negative deviation. So we have started with those ones that show positive deviation, and we have said that for positive deviation, the vapor pressure above the solution must be greater than that expected of an ideal solution. Now the next paragraph is explaining to us how does positive deviation come about, or how does positive deviation arise. So this is the explanation. Now what you should know is that there is absorption of heat from the surroundings when you are forming mixtures that deviate positively. We absorb heat, and the heat which is being absorbed is used to form weak intermolecular forces of attraction between unlike molecules of the liquid mixture. Now when those weaker intermolecular forces of attraction are being formed and heat is being absorbed from the environment or from the surroundings, it increases the escaping tendency of the liquid molecules of the mixture into vapor phase. Now as a result, you'll find that the vapor pressure above that solution is going to be higher compared to that predicted by Rorty's law, or that predicted by the ideal solution. So that's why we are saying positive deviation arises when the force of attraction, so you should note this, when the forces of attraction formed between unlike molecules of the components in the mixture are weaker. So the forces formed between unlike molecules of the components of the mixture must be weaker. Weaker forces of attraction are formed between unlike molecules of the components in the mixture than those between pure and separate components of the mixture. So we are saying that this is going to imply that heat is being absorbed. Now once this heat is being absorbed, as these weak intermolecular forces are being formed, that there's going to be an increasing tendency of escape of the liquid molecules into vapor phase. Now, when the liquid molecules evaporate into vapor phase, what happens? We are going to see an increase in the vapor pressure above the solution, but it's going to be increasing higher than that expected out of the Raoult's law. So let me hope you have understood that paragraph. So you're seeing the properties of the liquid mixture. Now, what do the properties of the liquid mixture that deviate positively from Raoult's law say? Now you'll find that we are going to pick all these properties from what you have already mentioned. So we are saying that the volume of the solution is always greater. Now I want you to realize that for positive, always volume is going to be greater. And once volume is greater, that means that heat is going to be absorbed. So you should note those two. So for mixtures that deviate positively, the volume of the solution is going to be greater than the sum when you add manually of the individual volumes of the components. So if you're given a question and they're giving you individual volumes of components, you add them, and if you find the volume of the solution being greater than the sum of the individual volumes, then that mixture or that liquid mixture is deviating positively from Raoult's law. Now you're saying that heat is absorbed. Remember that to form weak intermolecular forces of attraction, always heat is absorbed during formation of such forces, because for mixtures that deviate positively, they absorb heat from the surroundings or from the environment. Now we are saying that forces of attraction between unlike molecules of the components are weaker than those between molecules of the pure and separate components. Now, if you look at all these properties are the things that we have been talking about in the explanation. So let's proceed. Now, this is the vapor pressure composition diagram, and it's for a liquid mixture that deviates positively from Raoult's law. Now, remember, I've told you that for any mixture that deviates from Raoult's law, it's going to exert a higher vapor pressure than that predicted of Raoult's law, or than that expected of ideal behavior. In the previous video, we drew our ideal behavior phase diagram, and you saw that the curves were straight lines or horizontal diagonal running lines. So the ideal behavior is this, and the curve, when you are sketching, it should be in dotted lines. So the curve for a positively deviating solution is always curved, and it's always curved upwards. Let me hope you are seeing that. So to get the total vapor pressure, you get the summation of the partial pressure of A exerted by A plus the partial pressure exerted by B. Now your axis must be in terms of vapor pressure, and those axes must be labeled on both sides. Now for most of these diagrams in this video, we use mole fraction. Now notice that total mole fraction is always 1. So that means that where you see 1 here, that means that what we are adding, like B is going to be pure where 1 is, because it consists 100% of its composition. So that means that its vapor pressure is low. So the vapor pressure of B is low and the vapor pressure of A is high. Now notice that this denotation simplifies that this is the partial vapor pressure of B, the vapor pressure B exerts in its pure state. And this one here indicates that this is the partial pressure A exerts in its pure state. Now you realize that XB is at the peak. Now why is it at the peak? It's at the peak because this is where, remember, for mixtures that deviate positively, we form weaker forces of attraction between unlike components. So where the point picks off, this is where we form the weakest forces of attraction between unlike molecules. So pay attention to that. Now this is what we are going to be explaining in the next video. When you look at this graph is indicating that the more you are increasing mole fraction of B, the more the vapor pressure of the solution is increasing. And when you're going this side, the more you are decreasing the mole fraction of B, the more the vapor pressure of the solution also increases. So let's look at the detailed explanation. Now we are saying that the first diagram above, which we have just drawn, so I expect you to be following up your notes. Now I say, if you don't have the notes, you always pause the video. After pausing the video, you write down the notes. So you're saying that the first diagram above is showing that addition of liquid B to liquid A is going to result into an increase in the vapor pressure exerted by the solution. Now, why is that the case? Why is the vapor pressure exerted by the solution increasing as we are mixing these two components? And the components we are talking about is A and B. We are saying that the reason for that is due to formation of weak intermolecular forces of attraction. Now notice that these weak intermolecular forces of attraction are being formed between unlike molecules of the liquid mixture. Now, formation of these liquid weak intermolecular forces of attraction usually proceeds with absorption of heat from the surroundings. Now, when heat is absorbed from the surrounding, what happens? You will find that this heat that is being absorbed from the surrounding is going to come into the solution and increase the escaping tendency of liquid molecules, and these liquid molecules are going to go into vapor phase. Now in proceeding, that's why we get an increase in vapor pressure. So let me hope that has been simple to understand. So you're saying that at composition XB of B, the intermolecular forces of attraction formed are the weakest. Now when they are weakest, that means that at that point we expect a very high tendency of liquid molecules to escape into vapor phase, because to form the weakest intermolecular forces of attraction between unlike molecules of the liquid mixture, it's going to take a lot of absorption of heat. Now the more we absorb heat, the higher the liquid molecules, the higher the tendency of the liquid molecules escaping into vapor phase. Now once they do so, what happens? The more the liquid molecules escape into vapor phase, the higher the vapor pressure. Hence, we expect the vapor pressure at that point to be the highest, because the point at which the weakest intermolecular forces of attraction between unlike molecules of the components in the mixture are being formed. Now we are saying hence a maximum vapor pressure is being exerted. Let me hope you have got the explanation behind that statement. So in proceeding, we are saying that similarly, addition of A to B results into an increase in vapor pressure. Now notice that whenever we are adding one to the other, we are going to be forming weak intermolecular forces of attraction between their unlike molecules. And those weak intermolecular forces of attraction, they form with absorption of heat from the surroundings. The more we absorb heat from the surroundings, the more we increase the tendency of liquid molecules escaping into vapor phase. And the more the liquid molecules escape into vapor phase, the higher the vapor pressure exerted by that solution. So that's why you are seeing the curve going up, and that's strictly for mixtures that experience positive deviation. So we are saying that at composition XB, where the intermolecular forces of attraction formed between molecules are going to be the weakest. Now for boiling point composition diagrams, always when you're putting boiling point composition diagrams, we do this by fractional distillation. And the mean of fractional distillation was properly explained in the previous video. So if you didn't watch the previous video, you make sure that you watch how we explained fractional distillation. So we say for boiling point composition diagrams to be attained or to be obtained, we must fractional distillate. And here now what happens? You're going to find that components with higher vapor pressure are going to be the ones with the lower boiling point. Because if a component or a mixture has a higher vapor pressure, at any given temperature, it can easily counterbalance the external atmospheric pressure, hence boiling can easily take place compared to those components or mixtures with higher or with lower vapor pressure above their solutions or mixtures. So we are saying that the maximum vapor pressure at composition XB in the vapor pressure composition diagram is going to correspond to the minimum boiling point. Now, the higher the vapor pressure, the lower the boiling point. Like we have said that if you look at our vapor pressure composition diagram, we have seen a peak, and this peak here it had the highest vapor pressure if you look at your y-axis. So this one had the highest vapor pressure. Now the higher the vapor pressure, the lower the boiling point. So when you're doing a boiling point diagram, our curve is going to change. So that means that if our vapor pressure curve is like this, our boiling point curve is going to be V-shaped. And we are saying that at the same composition in the boiling point composition diagram. So let's hop on to the other slide and we see how we can hop on to the boiling point composition diagram. Now for the boiling point composition diagrams, you need to be very careful. When you're drawing these diagrams, marking is very strict. You always first start with labeling axes. So temperature must be labeled. After labeling temperature, you always include its SI unit, which is always degrees Celsius. Now your x-axis must also be labeled. In this case, I use mole fraction. You are going to find some books that use composition. You go with the one that you find easier because they all explain the same things. I told you total mole fraction is equal to 1. So after labeling two axes, you should also label axis this side, but I didn't include it here. Now you should put equilibrium signs in these curves to show that equilibrium is existing between these two. Now this is what we call a boiling point composition diagram. Now what I want you to notice is that the liquid phase exists in the lower side of your diagram and the vapor phase exists in the upper side of your diagram. Now we name the curves according to the phases that exist on each side. So the curves that are lower or that are below, we name them as the liquid. We name it as the liquid composition curve. And the curve that is above in the vapor phase, we name it as the vapor composition curve. So what happens? Now you'll find that they are all meeting at a point, and this point is where we have what we call an azeotropic mixture. Now we are going to define an azeotropic mixture later. Let's first look at what is happening. So that's how we label a phase diagram. Now notice that for positive deviation, our curve is going to be V-shaped, and this is our solution. The solution has the lowest boiling point, and that is T degrees Celsius. And the reason for that is because the solution exerts a higher vapor pressure. I told you the higher the vapor pressure exerted by a solution or a component, the lower the boiling point. And to get a boiling point composition diagram, you are always required to fractional distillate. So let's first talk briefly. Now, if you look at the x-axis, it's showing that increase in the mole fraction of B, what happens? So you're looking at variation of the boiling points of the mixture with increase in the mole fraction of B. So you're saying that the phase diagram above is showing that addition of liquid B to liquid A is going to result into a decrease, and the decrease is going to be in the boiling point of Y. The decrease is going to be in the boiling point of Y, where the composition of the liquid mixture is XB of B, and the mixture is going to boil at a constant minimum temperature of T degrees Celsius. Now, on your curve, the other thing I didn't talk about, you should label the boiling points of the pure components. Now, notice that at zero composition of B, that means that the other composition is 1. I told you the total mole fraction is always 1. So at zero composition of B, the other component is 1, or it dominates the whole mixture. So that means that if we fractionally distillate it, we are going to get its boiling point. And that's why we are saying that on this axis, we are going to label here the boiling point of A, and it's going to be also awarded half a mark. You also go this side and you label the boiling point of the pure component. Now here B is 1, that's why it dominates all the mixture. I told you total mole fraction is 1, so it dominates all the mixture. That means that boiling it at this point, you are going to get the boiling point of pure B. Now the other thing you have also noticed is that the boiling point of A is lower, whereas the boiling point of B is higher. Now why is that the case? If you go back to our vapor pressure composition diagram, you will see that A had a higher vapor pressure than B. So the higher the vapor pressure exerted by a solution or by a component, the lower its boiling point becomes. And the lower the vapor pressure exerted by the solution, the higher the boiling point becomes. The lower the vapor pressure exerted by the solution, the higher the vapor pressure becomes. So let's look at the next slide. So you're saying that similarly, now we are explaining the boiling point composition curve. So you're saying that Similarly, addition of liquid A to liquid B is going to result into a decrease in boiling point. Now, why is the boiling point decreasing? Remember that these are solutions that are deviating positively from ideal behavior. So when we say that solutions that deviate positively, they are absorbing heat from the surroundings in order to form weak intermolecular forces of attraction between unlike molecules of the mixture. Now, once they are forming those weak intermolecular forces of attraction between unlike molecules of the mixture, what happens? So you find that the more they absorb heat to form those weak intermolecular forces, the higher the tendency of escape of the liquid molecules into vapor phase. Now, when the liquid molecules are escaping into vapor phase, the vapor pressure above the solution is going to be higher. And I told you, when you apply at any given temperature, since there is higher vapor pressure above the solution, it's going to easily counterbalance the external atmospheric pressure such that boiling can easily take place. So the higher the vapor pressure exerted by any component or exerted by any mixture, the lower the boiling point, and the lower the vapor pressure exerted by any mixture or a component, the higher the boiling point. So we are saying, similarly, addition of liquid A to B results into a decrease in a boiling point of the mixture up to a composition XB of B, where the mixture boils at a constant minimum temperature. And I've told you that composition is where we have the azeotropic mixture, or you can call that point an azeotropic point. Now, what's the explanation behind this? The explanation behind this is what I've just mentioned. And we are saying the explanation behind that is because this shows that addition of one component to the other results into formation of weaker intermolecular forces. And these weak intermolecular forces are formed between unlike molecules of the components in that mixture, and they are formed with absorption of heat from the surrounding. Now, once heat is absorbed from the surrounding, we are going to be increasing the escaping tendency of those liquid molecules into vapor phase. Now, what happens when you increase escaping tendency of liquid molecules into vapor phase? There's going to be a general increase in the vapor pressure above the solution, such that the exerted vapor pressure, at any given temperature, exerted vapor pressure above this solution is going to become equal to the external atmospheric pressure. And once it becomes equal to the external atmospheric pressure, boiling is going to take place at a lower temperature, because the solution was already exerting a vapor before it was being heated. So you're going to apply a lower temperature for boiling to take place, because such a solution, its vapor pressure is going to easily counterbalance or become equal to the external atmospheric pressure. And once those two equate, boiling always takes place. Now, at composition XB of B, the mixture boils at a constant temperature, giving a vapor of the same composition as that of the liquid. Now, we are going to look at this more in details. So, we are saying that note the following. A liquid mixture of composition XB of B is going to be called an azeotropic mixture. An azeotropic mixture, now you should underline this or bold it. An azeotropic mixture is also called a constant boiling point mixture or an azeotrope, because when you boil such a mixture, you get a vapor of the same composition as that of the liquid. But whenever you're boiling that mixture, you make sure that temperature and pressure are kept constant. Now, if you look here, we are having an azeotropic mixture, and we are saying that an azeotropic mixture, now this is the true definition, so you should bold it or underline it. So an azeotropic mixture is going to be the liquid mixture in which at a fixed pressure and a fixed temperature is going to give a vapor on boiling of the same composition as that of the liquid. Now make sure as you are defining this statement, you're having a fixed pressure or a constant pressure, and you're having a constant temperature too, such that on boiling you get a vapor, and this vapor is going to be of the same composition as that of the liquid. Like I said earlier on, to get a boiling point composition diagram, you are always prompted to fractional distillate. So in this video, we are saying that for fractional distillation of a liquid mixture that deviates positively from Raoult's law, here are the stages that take place. Now notice that always don't forget labeling. So you always start by labeling your axis because they are given the marks first. Then you label your x-axis. After labeling your x-axis, you label the boiling points of the pure and separate components, like we explained in the previous video. Now, after labeling the pure and separate components, you label your phases. Now, here I forgot to include the phases. Always what is upward is called the vapor phase. The vapor phase is upwards, so you make sure that you include it, and the liquid phase is downwards. Now, after labeling the phases, you always label the curves, and you label the curves according to the phase in which it is curving towards. So these ones that are down, they are curving towards the liquid phase. So these ones are going to be called the liquid composition curve. Remember, it's a one curve. So the curve that is curving downwards is called the liquid composition curve. And the curve that is curving upwards or towards the vapor phase is going to be called the vapor composition curve. Now, what happens to these things on fractional distillation? Now, I want you to pay attention here. If you look at this curve, when we heat, always when we heat, I've already explained this in the previous video. When you are heating a component, you extrapolate your line and you extrapolate until you get to a point of interest. Like this point here, when you reach the what? When you reach the vapor, or when you reach the liquid composition curve, you draw a straight line which must be horizontal, and that straight line which is horizontal must be going to the vapor composition curve. Now when you go to the vapor composition curve, you always draw a vertical line going downwards, and that vertical line is always going to indicate condensation. So let's give a live example here. Now let me start with C1. If you look at C1, let me use a highlighter. If you look at C1, when you are hitting this thing, we extrapolate it using a dotted line. Now here we reached at the liquid composition curve. Now the moment you reach at the liquid composition curve, you draw a straight horizontal line, and this straight horizontal line you are drawing, you make sure that you touch it on the vapor composition curve. Now once it reaches the vapor composition curve, you condense that vapor. On condensing that vapor, condensing is the vertical line that goes downwards. So in condensing that vapor, you get a solution of C2. Now you repeat, and this is what we call progressive heating and cooling. So on heating this composition of C2, what happens? So we also do the same. We heat it, we draw a dotted line using a straight ruler, and that dotted line should reach the liquid composition curve. Once it reaches the liquid composition curve, you draw a straight horizontal line, and that straight horizontal line must go towards the vapor composition curve. Now, on the when you reach on the vapor composition curve, you condense that vapor, and on condensing that vapor, you get a liquid mixture. Now, here we got an azeotrope mixture. Now, you have to extrapolate such that you get the temperatures attached to those vapor that you got. So that was T1 and this was T2. Now you do the same thing towards the other side. If you look here, if you hit a composition of C4, what do? You get your ruler, you draw a line in dotted, and this line should go and touch the liquid composition curve. Once you reach the liquid composition curve, you draw a straight horizontal line. Now this straight horizontal line should go to the vapor composition curve. Now once you reach the vapor composition curve, you condense that vapor. So you draw a straight line going downwards so that to get a mixture. So here we are going to be describing these processes. Always when you do a straight horizontal line, you extrapolate that line so that you can get the temperature attached to it. And you do the same. Now when you hit C3, this is when you get this temperature. You draw a line to the liquid composition curve, then once you reach the liquid composition curve, you do a straight horizontal line towards the vapor composition curve. Now once it reaches the vapor composition curve, you condense. So let's look at the general explanation of what we have looked at. So generally, to explain this, they are telling us that when a liquid mixture, now pay attention to you need to open that diagram so that as we are reading this, you can review what you have been explaining. But this is what I've been explaining already. It has just been restated. So we are saying that when a liquid mixture of composition C1 of B is being heated, the liquid mixture is going to burn at the temperature of T1 degrees Celsius, producing a vapor of V1 degrees, producing a vapor which we named V1 if you look at your diagram. Now notice that to get this vapor, I've told you, you first extrapolate your line by heating, going upwards, and once that line reaches the vapor liquid composition curve, you draw a straight horizontal line towards the vapor composition curve. Now once you reach the vapor composition curve is when you label the vapor of V1. Now this V1, if you look at your x-axis, this V1 is going to be richer in B, so you should also include this, which is more richer in B. Now condensation of this vapor, condensation refers to that process where we draw a dotted line from the vapor composition curve where V1 is towards the x-axis at the bottom, and that is showing condensation to get a liquid. But remember that it's a straight vertical line, so we expect the vapor to have the same composition as the liquid which is being formed. So we say that the condensation of this vapor always produces a liquid, and this liquid is going to be of composition C2, and which is going to be similar to that of the vapor V1. So that's what I've just explained, because it's a straight vertical line. So you'll find that the composition of the liquid that is being condensed is going to be exactly the same as that of the vapor from which this liquid is being formed. Now we are saying that progressive heating and cooling, or progressive heating and condensation, is going to result into what? Now here they are telling you that if you repeat that process, what happens is going to result into obtaining the azeotropic mixture as the distillate, while liquid A remains the residue. Now I want you to pay attention to this. The distillate is the azeotrope because in positive deviation, the azeotrope has a higher vapor pressure. Now since it has the higher vapor pressure, that means that it's going to boil off fast, and is going to be corrected as the distillate on fractional distillation. However, liquid A is going to remain the residue. Now why are we saying liquid A, not liquid B? You should pay attention that you are always going to be explaining according to the sides you are on. So if you are this side on the boiling point of A is going to remain the residue, and if you're on the boiling this side, B is going to remain the residue. So pay attention to that. Now let's explain on the side of B, on the other half. So on the other half, we are saying that when a liquid mixture of composition C4 of B is being heated, it's going to boil at a temperature of T3 degrees Celsius, and that thing is going to produce a vapor V2. If you look at your diagram, that vapor V2 is going to be richer in A. If you look at your diagram, I've told you, I've explained everything. So we are saying that the condensation, condensation of this vapor is going to produce a liquid of composition C3, and this liquid of composition C3 is going to be similar. The composition is going to be exactly similar to that of the vapor V2. So pay attention to that. Now always when you are being prompted or when you are being asked to write these explanations, make sure that you always end your explanations with this statement, always. So we are saying that progressive heating and condensation results into obtaining. Progressive heating and condensation is going to result into obtaining, for positive deviation, it's always going to be the azeotrope or the azeotropic mixture. So for positive deviation, is going to be the azeotropic mixture that is always going to be got as the distillate, whereas liquid, the other liquid or the other half of the liquid you are explaining is always going to be the residue. Now note that this is going to be for positive deviation. So we are saying that note, and what are we noting? We are saying that liquid mixtures, other examples of liquid mixtures that deviate positively from ideal behavior are going to include the following. And we have looked at water and ethanol. We have looked at benzene and ethanol. There is also cyclohexane and methanol. There is carbon disulfide and ethanol. And there is tetrachloromethane and methanol. Now you are advised to know at least 3 or 4 of these, because sometimes when you are setting these questions, we can just mention the compounds. Now it's up to you to know whether those compounds deviate positively or negatively. But luckily, we give you calculations to calculate, so you can understand whether it's a positive deviation or a negative deviation still from calculations. So let's proceed to the next slide. So in this slide, you are being given questions to try out. Now here you're going to be prompted to draw those phase diagrams, and you're going to be prompted to explain them. Always make sure that if you want perfect chemistry, you try out as many numbers as possible, because you pass by practice and discuss with your friends. Now the question goes, the table below shows the boiling points of and mole fractions of methanol, and these boiling points or mole fractions of methanol and cyclohexane are in liquid and vapor phase. So we are saying that the boiling point of the pure and separate components, that is to say, pure methanol, is going to be 65 degrees Celsius, and the boiling point of pure cyclohexane is going to be 81 degrees Celsius. Now I've already told you that we mark those things, so you must indicate it properly and it must be well presented or stated. So always your boiling points of the mixture, this is going to be your y-axis, and you must make sure that you indicate it and you label it. Now these ones are going to be on your x-axis. One of them is going to give you the liquid composition curve, and it's these values that you are going to plot that are going to give you the liquid composition curve. Now when you're joining these points, join them using a free hand, because it must be a curve, the liquid composition curve, and it should be appearing exactly the same like we have been drawing them in the sketch diagrams that you have just took in your notes. So we are saying that mole fraction of methanol in vapor phase is this. So these values are going to give us the vapor pressure composition curve. And when you're plotting them, you also use a free hand, and you must get a curve and you must get a shape that is exactly the same or closely related, like the ones we have been drawing in the sketch diagrams. So we are saying that plot a boiling point composition diagram and label it fully. So you find that such a question is going to carry around 7 marks. And then part B, we have told you, or we have prompted you to explain, and you are required to explain the shape of the diagram. So your explanation must be in line with the explanation that I've given you, and I've always encouraged you, when you're explaining such things, you always make sure that you end with progressive heating and cooling. Even if it's paper 1, we need that statement. Always with issues concerning non-ideal solution. So progressive heating and cooling, we always need to see that sentence as the last sentence of your explanations. Now here we are saying, from your diagram, Explain what is going to happen when a mixture containing 0.2 mole fraction of cyclohexane is fractionally distilled. So what will happen there? Now you realize your x-axis is going to be mole fraction, is going to be in terms of mole fraction of methanol. But here they have given mole fraction of cyclohexane. Now how can you get the point that they want using the scale you used? So remember that the total fraction is 1, so you subtract 0.2 and then you get 0.8, and then you describe you hit. I've told you hitting, you draw a straight line going upwards. When it reaches your liquid composition curve, you draw a straight line going horizontally. When this straight line going horizontally reaches your vapor composition curve, you draw a condensing straight vertical line going downwards. And then you explain what is taking place. You extrapolate this horizontal line so that it can touch your y-axis, so that you can see the temperature at which that thing is going to be boiling. So everything there must be included. So you find that this one may carry 5 marks and above. So from your diagram, explain what will happen when a mixture containing 0.2 mole fraction of cyclohexane is fractionally distilled. So try out that question and you make sure that you present it to your respective teachers to be self-accountable of your work. So let's proceed to the next question. So in this next question, we are saying that you're going to be attempting the following. So this one is required to find or to state Rorty's law, and you have to mention its limitations. Now remember that we said that Rorty's law only applies for ideal solutions, and the limitations therefore you are expected to give must be in line with those of ideal solutions. So we are also telling you to state what is meant by an ideal solution. Always I told you, when you're defining an ideal solution, make sure that you include all the characteristics of ideal solutions. Don't write a short definition and you think you are going to get all the marks. So whenever you define the full definition and then you accompany that definition with all the characteristics or all the properties of ideal solutions. So number 3, you are prompted to explain why some liquid mixtures do not obey Rorty's law. And that's what we started with. This is the question we started with in these notes for non-ideal solutions. And we say that is due to the difference in the magnitude or strength of the intermolecular forces of attraction, first of all between unlike molecules and then the like molecules of the pure and separate components, which will in turn affect the escaping tendency of liquid molecules into vapor phase. And in this question here, you are being asked the vapor pressure of the solution containing 1 mole of A and 4 moles of B is this. So you're supposed to get mole fraction and then you get the individual partial vapor pressures. After getting the individual partial vapor pressures, you find the vapor pressure of the mixture by adding the two. And here they have told you to assume that it is ideal. Now they are telling you that state how the mixture deviates from Rorty's law, and you have to explain your answer. So you have to explain your answer in comparison to the pressure that you are given. So Roman number 3 is prompting you to calculate the composition of the vapor above the liquid mixture, assuming that that solution is ideal. And part C, you're going to be prompted to sketch a labeled boiling point composition diagram for a liquid mixture of those two components. So make sure you try your level best to note these questions down and you go back and you discuss them with your friends. If you find any difficulty, make sure that you consult or you see the teacher who is immediately close to you. Now, we are going to be looking at negative deviation as our next chapter or part of this topic. Now, for negative deviation, I want you to understand it's just the opposite of what we have just been looking at. So since we are saying that it's just the opposite, what is it all about now? We are saying that the negative deviation is going to occur when the vapor pressure exerted by the solution. Now remember that in the positive, we have said that it occurs when the vapor pressure exerted by the solution is higher. Now for negative, it's going to occur when the vapor pressure exerted by the solution is lower than that expected by the ideal solution or than that predicted by Raoult's law. So let's first look at the definition. So you're saying that negative deviation occurs when the vapor pressure exerted by the solution is less than that expected of an ideal solution or predicted by Raoult's law. Now we're asking how does the negative deviation arise? Now negative deviation is going to arise. Now remember that in positive deviation we say that forces of attraction between unlike molecules that are going to be formed when we are mixing the components are going to be weaker. Now, since we say that is the opposite of positive deviation, here forces are going to be stronger. Now, to form stronger forces of attraction between unlike molecules, such forces they are usually formed and they are accompanied by evolution of heat to the surroundings. Now, since heat is just evolved to the surroundings, it will hinder or it will reduce the effect of the liquid molecules to escape into vapor phase. That's why we are saying that negative deviation. Now, once liquid molecules are hindered to escape into vapor phase, what happens? So you find that the vapor pressure exerted above that solution is going to be lower than that predicted by Raoult's law or than that's being expected of ideal solutions. So let's first look at why solutions deviate negatively from Raoult's law. So for a solution that deviates negatively, this is how it comes about. And they are saying that negative deviation arises when the forces of attraction formed between unlike molecules of the components of that mixture are going to be stronger. Those forces are going to be stronger than those between molecules of the pure and separate components. Now we are saying that this therefore implies that heat is being evolved, and as heat is being evolved, that means that heat is only evolved when we are forming stronger intermolecular forces of attraction between unlike molecules of the mixture, and once they are formed, the escaping tendency of the liquid molecules into vapor phase is going to decrease. So the escaping tendency of the liquid molecules into vapor phase decreases. And this is going to result into lower vapor pressure because less liquid molecules are escaping into vapor phase. That means that the vapor pressure that is going to be exerted above that solution or at the surface of that liquid is going to be lower than that expected or than that exerted by Raoult's law. So let's look at the characteristics or properties of mixtures that deviate negatively or positively from Raoult's law. Now these properties or characteristics are going to be exactly different from those of the positive deviation. That's why we are saying that heat is going to be evolved during formation of the solution. For positive deviation, heat is absorbed. Reason being, For positive deviation, we are forming weak intermolecular forces of attraction between the component, unlike molecules of the components of the mixture. But here we are forming stronger forces, and formation of stronger forces proceeds with evolution of heat from the solution. And once heat is being taken away from the solution, volume of the solution is going to be lower. Volume of the solution is going to be lower. For positive deviation, volume of the solution was higher than the sum of the individual volumes of the components. And we are also saying the forces of attraction between unlike molecules of the components are going to be stronger than those between pure and separate components of the mixture. Now here is the vapor pressure composition diagram for a liquid mixture deviating negatively from Raoult's law. So as we said, you always first start with labeling axes. So the y-axis is good for the vapor pressure composition diagram. The y-axis is always in terms of vapor pressure. You have to label it on both sides, and then you label your x-axis. X-axis for this video we use mainly mole fraction. You'll find other videos that are using. You find other pamphlets or textbooks that are using composition. They are all the same thing. For composition we use percentages. For mole fraction we use 0 to 1. So at 0 mole fraction of B, always the other pure substance is present, which is A. That's why we are saying that this is going to always this symbol denotes vapor pressure of A exerted in its pure state, and you should also label it because it carries a mark. And always this one indicates the vapor pressure of exerted by B, and you should always also label it because it also carries a mark. Now always the hydro behavior, you draw it and you sketch it in dotted line to indicate that it's not part of our diagram, but you're just using it to compare it to our curve. So the hydro behavior is always diagonal and you draw it in dotted line. So naming it will also carry a half a mark. So this is going to be our curve for a negative deviation. Now for negative deviation, our curve is showing that the more we are adding B, the lower our vapor pressure is becoming. Let me hope you are seeing the curve sloping down. And the total vapor pressure of this solution is going to be equal to the vapor pressure of A plus vapor pressure of B. But notice that this is not going to be the case with negative deviation. Now at this point, this is where the forces are the weakest. Sorry, for negative deviation, we are forming strong forces. So this is the point whereby forces are the strongest because it formed the lowest peak. So let's hop on to the explanation part. So for the explanation, we are saying that the vapor phase above shows that addition of liquid B to A results into a decrease in the vapor pressure exerted by the solution. Now briefly, let's first talk about this. We say that for solutions that deviate negatively, when they are being formed, first of all, we are forming stronger intermolecular forces of attraction, and these intermolecular forces of attraction, they are getting formed in the unlike molecules of the components present in the liquid mixture. Now, as these forces of attractions are forming, they form with evolution of heat to the surroundings. Now, since the heat is leaving the solution, the tendency of the liquid molecules present in that solution escaping into vapor phase is going to be reduced. And once it's being reduced, the vapor pressure exerted above that solution, above the surface of the solution, is going to be decreasing. And the lower the vapor pressure, the higher the boiling point. So when you go to boiling points, you are going to be looking at that. So we are saying that the reason behind that is because this is due to the stronger intermolecular forces between the unlike molecules of the components of the mixture. So we are saying that at composition XB, what happens at composition XB? At composition XB of B, if you look at the second paragraph, at composition XB of B, the intermolecular forces formed are the strongest. Now, since they are the strongest, that means that there is a very low tendency of liquid molecules escaping into vapor phase. And once that happens, that means that we have the lowest vapor pressure at that point. And once vapor pressure is too low, that means that the boiling point of that solution is going to be very high, because it's going to take a very high temperature to evaporate off those liquid molecules, so that vapor pressure above the solution can counterbalance the external atmospheric vapor pressure for boiling to take place. We are saying that hence a minimum vapor pressure is exerted. Now let's proceed. We are saying that similarly, addition of A to B results into a decrease in vapor pressure up to composition of XB, where forces of attraction between unlike molecules of A and B are the strongest. So let's first look at the boiling point composition diagram. Now remember that the vapor pressure composition diagram always gives us a hint on how the boiling point composition diagram for our liquid mixture is going to behave. So that's why we are saying that for the boiling point composition diagram of a liquid mixture that's going to deviate negatively from what is law, this is going to happen. We are saying that the minimum vapor pressure at composition XB of B in the vapor pressure composition diagram is going to correspond to the maximum boiling point. That means that our azeotrope is going to have the highest boiling point, and we have given a reason for that. Reason being, in the vapor pressure composition diagram, it has the minimum vapor pressure. So the minimum vapor pressure in the vapor pressure composition diagram always corresponds to the maximum boiling point in the boiling point composition diagram. So let's look at the science behind that. So always corresponds at the same composition in the boiling point composition diagram. So as already explained, when you are drawing these diagrams, always start with axes. You start with labeling your axes. After labeling your axes, like I've explained, the lower phase or the low, we put the liquid phase, and the up exists our vapor phase. Now when you're labeling, you label curves according to the phase that exists in that region. So that's why the curve that curves downwards in the liquid phase, we name it the liquid composition curve. And the curve that curves towards the vapor phase, we name it as the vapor composition curve. So make sure that you do not forget the two. So the point where our curves meet is where is going to be our azeotrope mixture, and this point can also be called azeotropic point. So we are going to be looking, whenever you are given mole fraction, or is at 0 mole fraction of B, implies that the other component is present in its pure state. That means that whenever we boil such a fractional distillate, such a compound is going to give us the boiling point of the pure component, which is A, and labeling that is going to carry a half a mark. Also, this is going to give us the boiling point of pure B, and labeling it is going to carry a half a mark. So always try to indicate the equilibrium signs to show that equilibrium exists at any given point between these curves. However, you can also ignore it. So let's proceed on to the next slide and we see how we can best explain this graph. So for the explanation, we are saying that for the first diagram above, for the boiling point composition diagram above, it is showing that addition of liquid B to liquid A is going to result into an increase in the boiling point of Y. Now, why is this the case? Now, remember that this is negative deviation. The explanation is always going to remain the same. When you are adding a liquid into the other, for liquids that deviate negatively, first of all, you are going to be forming stronger intermolecular forces of attraction between unlike components between unlike molecules of the components in that mixture. And formation of those stronger forces usually proceeds with evolution of heat. Now, once heat is evolved, the escaping tendency of our liquid molecules from this liquid mixture is going to reduce. That means that above the surface of that liquid mixture, there is going to be a very low vapor pressure than that expected from Raoult's law. Now, once there is a very low vapor pressure above the solution, that means that for such a solution to boil, we need a higher temperature, or we need increased temperature. The more we mix the components, the more temperature we need for such a solution to boil. So you find that at any given temperature, boiling is going to take place at a very higher temperature compared to the pure boiling points of the pure and separate components. So that's why we are saying that results into an increase in the boiling point up to point Y. And we are saying that where the composition of the liquid mixture is XB of B. Now point Y can also be called an azeotropic point because that's where we form our azeotropic mixture. We said an azeotropic mixture is a liquid mixture which when heated at a constant temperature and pressure is going to give us a vapor, and this vapor is going to be of the same composition as the liquid mixture that we heated. So always don't forget that. And we are saying that and the mixture is going to boil at a constant temperature to degrees Celsius. So similarly, we are saying that addition of liquid A to liquid B is going to result into an increase in the boiling point of the mixture up to composition of XB of B. And this is a composition where the mixture is going to boil at a constant maximum temperature, which is 60 degrees Celsius. So let's look into the explanation for this. We are saying that this shows that addition, now this is what I'm from explaining. This is showing us that addition of one component to another is resulting into formation of stronger intermolecular forces of attraction. And those forces of attraction, they are usually formed between unlike molecules of the components present in the liquid mixture. And once they are formed, they occur with evolution of heat to the surroundings, and in turn, the escaping tendency of the liquid molecules from the solution is going to be reduced. So they are not going to be evaporating into vapor phase. Once it's reduced, that means that at any given temperature, for such a solution to boil, the exerted vapor pressure becomes equal to the external atmospheric pressure, but it's going to become equal to the external atmospheric pressure at a very higher temperature, corresponding to higher boiling points. Let me hope you have got that explanation. The lower the vapor pressure exerted by the solution, the higher the boiling point of that solution will become. So we are saying that at composition XB, at composition XB of B. Now remember that that's where the azeotropic mixture is formed. The mixture is called an azeotrope, and this is a mixture which at constant temperature and pressure is going to boil to give us a vapor, and this vapor must be of the same composition as that of the liquid. So always don't forget that. Now we are saying that fractional distillation of a liquid mixture that deviates negatively from Raoult's law. Like I told you how to explain those ones that deviate positively from Raoult's law is the same thing that we take on here, and it's the same procedure that we proceed on with. So we are saying that consider the following boiling point composition diagrams for a liquid mixture of A and B. So if we are to consider that, how are we going to come up with the conclusions? So we are saying that, as we said, when you're drawing these curves, you always make sure that the axes are well labeled. Make sure that you label temperature on both sides, because that one will carry a mark. Now also in this graph, I didn't label the states. We said the state that appears up here is always called the vapor phase, and the phase that appears down is always called the liquid phase. Now we name curves according to the phase they are curving outwards to. So this one, which is curving outwards to vapor phase, is going to be called the vapor composition curve. And this one, which curves towards the liquid phase, is always going to be called the liquid composition curve. They also carry half a mark each on labeling. Now, since our x-axis is in terms of increasing B, total mole fraction is always 1. So at 0, that means that the other component is in its pure state. That's why we have the boiling point of pure A, and which is denoted here. And we also have boiling point of pure B, and which is denoted here. Labeling those pure boiling points also carries a half a mark. So always make sure that you don't forget. Now, when you are explaining these things, the concept is going to remain the same. You draw, here you draw, like if you're eating composition C2, if you're to eat composition C2, you draw a line going upwards. The moment you reach your liquid composition curve, you stop, and then you draw a straight horizontal line, and this straight horizontal line must come and touch the vapor composition curve. On touching the vapor composition curve, condensation takes place. You cool this vapor you have got. Now in this case you have V1. So you cool this vapor. On condensing it, you are going to get a liquid mixture, and this liquid mixture is going to be of composition C2. Now what happens when you heat this C2 again? Now this is what we call progressive heating and condensation. When you heat C2, still you draw and extrapolate through that line, that very line, to the boiling. When you're heating, you stop on the liquid composition curve. Once you reach on the liquid composition curve, you get your ruler and you do a straight line towards the vapor composition curve. On reaching the vapor composition curve, you extrapolate downwards, you condense. Going downwards is called condensing. And then you get another composition, and you repeat the same thing. That's what we call progressive heating and cooling. Now this is our azeotropic point, because it's a point where the azeotropic mixture is being formed, and I told you never to forget that. And then here we do the same thing. If you hit a liquid mixture of composition C3, you draw and extrapolate. The moment you reach a liquid composition curve, you stop. And from there, once you reach the liquid composition curve, you draw a straight line. This straight line must go towards the vapor composition curve. Now, in going towards the vapor composition curve, you get a vapor, and this vapor is going to be V3. So you condense this vapor. Now, on condensing this vapor, you always get a liquid of composition C4. Now notice that the vapor and this liquid are going to be of the same composition. So this is heating, going upward is heating. Once you reach the liquid composition curve, you draw a straight line in dotted, and it must touch the vapor composition curve. Once you get the vapor, you label that vapor. You're also allowed to label the temperature at which that thing happens. And then you cool it and you condense it. Condensing it is going downwards. So you extrapolate and you label this temperature. You also extrapolate these curves and you label this temperature. You also extrapolate this and you label that temperature. So this is what you are going to be looking at as an explanation in our next slide. But make sure your curve is well labeled. So we are saying when a liquid mixture of composition C1, like follow up your diagram because this is what I'm from explaining. When a liquid mixture of composition C1 of B is being heated, it's going to boil at a temperature to 1 degree Celsius. Now I didn't include this temperature, but make sure that you extrapolate it and you put it there, just like the way I've just sketched in the diagram. It produces a vapor of V1. Now you get this vapor of V1 after drawing that horizontal line, and it must be dotted. And this vapor is going to be more richer in our mole fraction, which is increasing. So which is more richer in A. If you compare this with the mole fraction that we had downwards, you will see what I'm talking about. Compared to the composition of the liquid mixture C1. Now we talk about condensation. Condensation is when you are from that vapor composition curve. Now you are drawing a dotted line towards the x-axis so that you can see the composition of the liquid mixture you are getting. So you are saying that the condensation of this vapor produces a liquid, and this liquid is going to be of composition C2, and this composition is going to be similar to that of the vapor, which is called V1. Now we are saying that progressive heating and cooling. What will happen to progressive heating and cooling? Progressive heating and cooling, or progressive heating and condensation, results into obtaining pure A as the distillate, and the azeotrope is going to be the residue. Why is our azeotrope the residue? Reason being, in this case, for negative deviation, azeotropic mixture is the residue because it has the highest boiling point, and for fractional distillation, always the distillate must have a lower boiling point. So for mixtures that deviate negatively, you find that the individual components are having a lower boiling point compared to the mixture that is being formed. And to determine what is going to remain as the distillate, you determine the curve or the part of the curve you're explaining. If you are on the side of the boiling point of pure A is going to be the distillate. If you're on the side of boiling point of pure B is going to be the distillate. Let me hope. Always I've told you, when you're being told, even in paper 1, even in paper 2, you must end your sentences with this. This is very important. It's the closing section of your explanations, however small the marks allocated may be. So take notes. So proceeding, we are saying that when a liquid mixture, of composition C3 is being heated, it's going to boil at a temperature, and the temperature at which it's going to boil is 30 degrees Celsius. Now I didn't indicate this temperature, so you go back onto your diagram and you indicate that temperature, producing a vapor, and this vapor is going to be V3, which is richer in B. Condensation of this vapor produces a liquid of composition C4. The reason why I'm not explaining much is because I've already explained all this on the diagram itself. So producing a liquid of composition C4, which is similar. Always on condensation, we must get a liquid mixture having a similar composition as our vapor V3. So we are saying, as usual, this one is always the closing tag. progressive heating and condensation. Progressive heating and condensation is going to result into obtaining liquid B as our distillate, because we are on the half of liquid B where we place pure boiling point of B. So take note of that. So that's why we are saying that liquid B is going to be our distillate in this case. If you are from that side, where the azeotrope is always going to be the residue, but note that this is strictly for negative deviation. So let me hope you have understood that curve. For any inquiries, you type your questions in the comment section. In this slide, we are looking at notes, and in this note, we are giving you examples of liquid mixtures that deviate negatively from Raoult's law. I've told you, you need to know about 3 to 4 because it will help you. It will help you first of all in the explanation numbers of paper 2 chemistry. You will be able to differentiate and not to be tricked like other students may be tricked. So it's better to pay attention. You read and you give it enough time, and you know some good number of examples that deviate negatively and those that deviate positively, as I've given each and everything in this video. So we are saying that one of them is going to be chloroform or trichloromethane and propanone. The other is going to be phenol and phenylamine, and the other is going to be nitric acid and water, and the other is going to be hydrochloric acid and water. Now what you should note about negative deviation is always those things that are going to form intermolecular hydrogen bonds that experience negative deviation. And always intermolecular hydrogen bonds are formed, strong intermolecular hydrogen bonds are formed between a very highly electronegative element and hydrogen atom. The only highly electronegative atoms we have in the periodic table is nitrogen, oxygen, and fluorine. So anywhere where those things are present, nitrogen, oxygen, and fluorine, if any of those atoms bonds with hydrogen, they form what we call strong intermolecular hydrogen bonds. So for those of you who are confused, let me hope you have paid attention to this. So proceeding, we are going to be looking at the graph. Now for this one, we are saying that for the liquid mixture of chloroform, for the liquid mixture of chloroform and propanone. Now I only picked one example to explain. We are saying that for the liquid mixture of chloroform and propanone, both the components are going to be polar compounds, but carbon to oxygen double bond in propanone and carbon to chlorine bonds in chloroform are going to be polarized. So we are saying that when the two compounds therefore are mixed, the negative charge on the oxygen atom of propanone and the positive charge on the hydrogen atom of chloroform are strongly attracted, and as a result, we are going to be forming hydrogen bonds, just like explained. And then you present a simple sketch. Now, this question is very common among the questions that they present for explaining negative deviation in paper 2 among the explanation questions. So always keep your eyes awake. I've given you a general example of how you can explain together with a sketch. This is what we call the intermolecular hydrogen bonds formed between a very high electronegative element and an hydrogen atom. And we only have 3 electronegative elements: nitrogen, oxygen, and fluorine. So pay attention to that, and the structure was well labeled. What happens? We are saying that therefore that is going to result into evolution of heat, because the hydrogen bonds that are being formed, remember hydrogen bonds are stronger bonds compared to the bonds between the pure and separate components of what you are mixing. So that's why we are saying this is going to result into evolution of heat because the hydrogen bonds that are being formed are really stronger than the van der Waals forces of attraction holding those two pure and separate components. And in this case, we had pure propanol and pure chloroform. And then we looked at another example, and then we say that for the liquid mixture of nitric acid and water, what happens there? There's what we call ionization of the covalent molecules of the acid in water. So you find that nitric acid is going to ionize to give us hydrogen ions and nitrate ions. So as this happens, as the formed ions are hydrated, stronger ion to dipole attractions are being formed. Now, once stronger ion to dipole attractions are being formed, you find that the van der Waals forces of attraction in nitric acid and the hydrogen bonds in water molecules are going to be formed. And as a result, there will be evolution of heat and consequently a reduction in volume of the general solution. So you also pay attention to that. Now let's look at azeotropic mixtures. Now for azeotropic mixtures, there are two. We have what we call the minimum boiling point azeotropic mixtures. And then we also have what we call the maximum boiling point azeotropic mixtures. Now notice that for positive deviation, our curve was V-shaped, our boiling point composition curve. So here, at the point where these two, I can say oval-shaped diagrams meet, or shapes meet, is where we form our azeotropic mixture. That means that positive deviation is one which gives us the minimum boiling point azeotropic mixture, and the negative one, always we had an inverted V. Where these oval shapes meet is where we form our azeotropic mixture, and that point is called the azeotropic point. Now this is where we form maximum boiling points according to our boiling point composition diagrams. So the negative deviation is what gives us this. Let me hope you have understood that explanation. So let's proceed on to the next slide. Now for the next slide, we are saying that these are going to be the differences that are going to exist between these different types of azeotropic mixtures. And we have the maximum boiling point azeotropic mixture and also the minimum boiling point azeotropic mixture. And we are saying that the maximum boiling point azeotropic mixture, we say that that one is obtained from negative deviation. So you always give characteristics for negative deviation. So always is obtained from liquids that mix and deviate negatively. So that's where the point came from. And the other one is going to be the opposite, obtained from mixtures that deviate positively. And the other second point is boiling point is higher than that of the individual components present in the mixture. Like for negative deviation, hope you look at the boiling point composition curve, you'll find that the azeotrope boils at a very higher boiling point compared to the individual components present in the mixture. And this is the opposite for the other, for the minimum. Its boiling point is always lower than the boiling point of either of the components present in the mixture. So we are saying that this one is obtained as the residue. Always, since in negative deviation, the azeotrope is the one with the highest boiling point. So on fractional distillation, it's always going to be our residue. Whereas the minimum boiling point azeotrope is going to be obtained as the distillate during fractional distillation. Let me hope that is self-explanatory. So these are some of the three differences and they are very examinable. So make sure that you don't forget any. Now here we have given examples of mixtures so we are saying that azeotropic mixtures behave like pure substances or compounds in the following ways. Now always remember that these ways are having conditions, like you are saying fixed. So don't miss out those conditions. So we are saying that both have fixed compositions, but these fixed compositions only occur at a condition, which is a constant pressure. So azeotropic mixtures, they are going to have fixed compositions only at constant pressure. And also, azeotropic mixtures are going to have fixed boiling points, and this one is only going to become true only if the pressure is kept constant. However, if pressure is not kept constant, they are going to vary. That's why we came up with this heading, and we say that differences between azeotropic mixtures and pure compounds. What is going to make them different from the pure compounds? So first of all, their points are same as our eutectic, so you don't confuse them. Azeotropic mixtures can be separated by physical means. Now remember that we can't separate compounds by physical means. Compounds are always separated by chemical means, but for azeotropic mixtures, they can be separated by physical means. Now azeotropes cannot be represented by a general formula, whereas compounds can be represented by a general formula. For azeotropes, there is no way you can write a formula like that one for magnesium oxide. So for azeotropes, they can't be represented by any general molecular formula or simply a molecular formula or a chemical formula. You can't write down their formula like you can write for a compound such as magnesium oxide, such as sodium oxide, such as chromium oxide, among others. And if you look at point 3, the boiling point and composition of azeotropes changes or varies with changing pressure. So also take note of this. The boiling point and composition of the azeotropes changes or varies with changing pressure. Now we are saying that the freezing point of an azeotropic mixture always takes a wide range of temperatures, while the freezing point of compounds always takes a narrow range of temperatures. So to be on the safe side, always make sure that you know at least 3 of these ones, but I advise to know all. Of the methods, azeotropic mixtures can be separated. Now you can be asked any of these methods. So you choose the one, you should know like 3. You should know a minimum of 3. So one of them refers to the distilling with the third component, and we shall look at all of these ones in details, and we also perform calculations about them, and I think that will be in the next video. So I think that the third component should mix with one of the components of the azeotrope to form an ideal solution, and it must be miscible with the other component. So take note about that. So these are just brief notes to introduce the topics that we are going to cover in details. So we are saying that the mixture is then separated using a separating funnel. So we are going to look at this under solvent extraction. So the components of the ideal solution are separated by fractional distillation, and the azeotropic mixture of ethanol and water can be separated by addition of benzene. So that's about distilling with a third component as one of the methods of separating azeotropic mixtures. Now let's look at the chemical method. What can you say about the chemical method? For the chemical method, we are saying that Roman number 1 can be divided into 2. You can either use chemical method by adding another component that has stronger affinity, that has a stronger affinity for one of the components of the azeotrope. For example, in an azeotropic mixture of water and ethanol, calcium oxide can be added to combine with water, and the mixture is eventually filled. Now the filtrate is always, now this is not filled, it's filtered. Now the filtrate is always redistilled to obtain 100% pure ethanol. Then Roman number 2 of the chemical method, you can also use adsorption. Using adsorption, now in this case we are going to be using charcoal or silica gel, can be added to adsorb or to absorb and retain any of the components of the azeotrope. Now lastly, for the case of this video, we look at solvent extraction. Now solvent extraction, this is our next heading in the next video. So we are saying that one of the components in this case can be obtained by adding a solvent in which it is more soluble than the other. So we are going to be looking at this in details in our next video. So these are some of the trial questions to help you master and examine yourself about the understanding of the topic. Now what you're going to do, you're going to pause the video and you take individual questions on each and every slide. So pause the video and you take the questions. I'll just be scrolling through the questions. I think they're about 3 or 4 because I've explained everything. So pause the video and take the questions. That's it for this video. The video has been presented to you by Walgembe Yusuf. Now reach me out of any inquiries about chemistry or mathematics. You can reach me out on the following telephone numbers, and you advise to encourage your friends or to refer your friends to this channel so that you can view content and you help each other as a family. For those of you having exams, I wish you success in your exams. Now, for any inquiries, you are advised to write a note in the comment section. So let's meet in the next video about solvent extraction.